Hi everyone. Alright, let's get started now. The clock is already ticking. I'm Lecция Dubrov. I'm an associate professor of Southern Federal University, and what I'm going to talk about is my course, Metaprogramming with C++. First I'm going to talk about some formal characteristics of my course, the audience, and so on. And then we will move to the some applications of metaprogramming. What is it for? And next I'll give you some short conclusion. The course is intended for the informational technology students of the third year. It has some lectures and some practice. Some lab hours, and the entry level for the students should be the familiarity with such courses as programming fundamentals, programming languages, and operating systems. So, what are the goals? The course should teach the students how to apply some means of C++ properly to use in everyday life. So actually, if you look at these goals, you will see that there is a little trick there. Metaprogramming is just a part of this course. It's not the whole part of this course, but all the parts are somehow interconnected. So, first we are going to look at polymorphism. We are going to study, for example, Liskov substitution principle, and we are going to look at the general ways how to use polymorphism in everyday life, how to use it properly, which is more essential. Then we will move to the big topic, resource management. Here we study, among other topics, smart pointers and exception safety. We will look at the general exception safety guarantees, how to achieve them, and how the standard library is fit to these requirements. Next, we will cover a little, a small topic named multi-threading. We will look how we can use such means as resource management, templates to facilitate metaprogramming with C++ 11 or with Boost library. Then we will move to template metaprogramming, and the main goals here are generic programs. We will teach students how to write them, then design patterns, and domain-specific embedded languages. So, the lecture plan is here, you can look at it. Here we study polymorphism, exceptions, dynamic memory, resource management, smart pointers, and so on. And the second part consists of templates. It is related to templates. We will study NPL library in depth here, design patterns, and some applications of metaprogramming. We also have labs. So we create programs that use polymorphism, exception safety. We design exception-safe containers here. We use multi-threading to solve some common tasks. We use, finally, we use meta computations for constant computations and type computations. That is for the formal plan. And now I'm going to cover a little bit at a glance one topic called metaprogramming. So, There are three, or maybe we will cover two here, the two topics here. First is generic code. So I want to show you this example. Let's consider that we have some algorithm which is generic. We want it to be generic. But we should teach it to work with different types. And we can mention here that some of these types are better passed to this algorithm by value. Which are these types? Can you name them? No. More generally.
Primitive, atomic.
It seems to me this is a building types. Except the last one.
Small structure.
Value types. I think these are value types, and not reference types.
The rule of the thumb is that all types that are trivially copyable and which size is not so big. So we see some fundamental types, pointers, arrays, because arrays are passed anyway by pointers. And we have some small structures, trivially copyable structures. But if we have big structures, we should, here it is better to pass them by constant reference, right?
Only in the case if we would like to save the formal view of our grammar, because we could use the pointers for the same case.
Yes, but anyway, we should use either pointers or references. References are more convenient here, yes?
But reference hides the situation when we change our parameters.
Why?
We don't change it, it is constant.
In this sense.
Yes,
In
it is
this
constant.
case.
If
Yes.
we want to change something, we just emit the constant keyword.
So we should mention that this algorithm doesn't change its formal parameters.
Yes,
That's important. Then we should pass some types with non-trivial copy constructors because they are called here. Otherwise, they should be called here, and these are extra work that we should avoid. And if the types are non-port, not non-plain old data, here we are at danger of type skewing. If we pass, let's say, a rectangle, which is the derivative of shape, here a copy of shape would be created, and this would be incorrect. So we would like to write a template, right? But we cannot do it really because there are different types of types. Yes. So what should we do? Here comes meta function computations. Here we see a meta function called best param type, which has an input as any type, and its return type, it returns conditionally a type. It returns the copy of this type if the input type is an array type, or it is trivially copyable and its size is less than the size of a pointer. You can see that. Otherwise, it returns the constant reference to this type. When we use the NPL library, I can mention here, we can do even better. We can write here identity of T, and here we can write something like add constant reference, not to instantiate these types if we don't need them. So, how can we use this meta function to write our algorithm? We can call it here, and the body of this algorithm is just some code for testing purposes. We are writing if it is the type of T is a reference, and we write its name here. And how can we test this algorithm? So we have a structure with non-trivial copy constructor. we have a polymorphic structure, non-pod structure, we have a simple structure which is small, and another simple structure which is a little bit more than the size of the pointer. And we have a normal variable and an array of these variables. Right? Do you have any questions here? No? So let's move on. So when we are ready to test our algorithm, we are calling it, and it types us whether it is passed by the reference and the name of these types. You can see that some of them are passed by reference or by value. Alright, let's move on. So, another example. Matrix computations. If you are a good expert in matrix computing, you definitely know this library BLAS, basic linear algebra subroutines, right? When we call these functions in C language, what does it do? It is difficult to remember, it is impossible to guess what does it do, but essentially it does the same. You can see that this is a kind of domain-specific embedded language. Domain-specific embedded language is the language which the programmer creates for his own needs, and it has very narrow field of application. So this expression is rather obvious, is much more obvious than the left one, and it does actually the same. So this function calculates these matrices and coefficients using this formula. But we would like to write this one. But what prevents us from this?
I think non-efficient realization.
Yes.
I think.
Yes, the efficiency. The efficiency is a big problem of the right example. So let's move on to the same example, but a little bit simplified, the vectors. But the essence of this example would be the same. So, if we compute A plus B plus C, what happens? What happens here? Why?
Some additional variables will
Yes.
be created during
Yes.
this process.
Yes. If we
It will be not
create
so
this,
effective.
yes, if we create this overload operator, we have vector which is a temporary variable. It is created, it is destroyed, and it is a big source of inefficiency. But we can intuitively we can realize that this sum could be made just straightforward. X first is A first plus B first plus C first. There are no temporary variables here. So what could we do here? There is another approach, a metaprogramming approach. So we can construct, instead of temporary objects, we can construct expressions which are the compile time formulas we want to do. So these expressions are lazy. That means that they are evaluated up to the end. They are evaluated only at that point that they are needed. So I won't go into detail because of the lack of time, but essentially what does this example? It constructs the compile time type, which represents the tree, the computation tree of this formula. And we can also define some extra structures to calculate this formulas when they are needed, at the very moment when they are needed. That means they are needed just here. They are computed recursively. So, to wrap up this lecture, we can see that the main goals, the main skills that students achieve from our course is a better proper polymorphism use, much more easier than manual correct resource management, employing multiple threads, using constant and type computations to implement generic algorithms, using policy-based design patterns, and implementing domain-specific embedding languages. And now I have a little bit more time. I can show you some fun, some joke from the field of domain-specific embedded language, which I have found on this website. So you see the example is called analog literals. Analog literals are such constructs that represent values, integer values in lengths. The length of these segments is proportional to the value. So you can see, and this, what is more important, I can stress that these values are compile time values. So they are computed by the compiler before the program starts. Yes, but
the first minus is binary and the others are unary.
probably
Right?
you can go to this website and check for details. But this is not the whole picture. We can also use this language to express areas. So we can express two-dimensional values, and we can compute areas from these two-dimensional values and compare them, and so on. We can assert that these areas are equal to each other, and we can apply this to visually to visualize our language, our code. But this is exactly not not enough, because we can also represent three-dimensional values in such a language, and we can also compute the volume, and we can assert that it's equal to the area of its top edge to the length of one of its sides, and so on. So we can get a top of this three-dimensional shape, and we can also store it in, well, if we store it in explicitly, we should provide the type, which is not good because it already has these values as numbers. But we can use the C++11 feature to compute types at compile times. So that's it. Thank you for your patience. Now if you have any questions, I'm glad to answer them.
Actually, I